Hello, can everyone hear me? I'm going to be learning C++ again. Uh, Hold on, let me just change the first screen. Uh, Wait a minute. Okay, so last time I finished chapter 3. This time I'm going to start with chapter 4, Introduction to Fundamental Data Types. I think the entire chapter is about data types. And maybe I might do chapter 5 this stream as well. Okay, right. Introduction to Fundamental Data Types. Bits, bytes, and memory addressing. In lesson 1.3, we talked about the fact that variables are names for a piece of memory that can be used to store information. It is my avatar working properly? Yeah, I don't see any issue. To recap briefly, computers have random access memory that is available for programs to use. When a variable is defined, a piece of that memory is set aside for that variable. The smallest unit of memory is the binary digit, which can hold a value of 0 or 1. You can think of a bit as being like a traditional light switch. Memory is organized into sequential units called memory addresses. Similar to how a street address can be used to find a given house on a street, the memory address allows us to find and access the contents of memory at a particular location. Each memory address holds 1 byte of data. A byte is a set of bits that are operated on as a unit. The modern standard is that a byte is comprised of eight sequential bits. The following picture shows some sequential memory addresses along with the corresponding byte of data. So address 3 stores this, address 2 stores this. Okay. Some older non-standard machines may have different bytes of a different size. However, we generally need not worry about these. Because all data on a computer is just a sequence of bits, we use a data type to tell the compiler how to interpret the contents of memory in some meaningful way. You've already seen one example of a data type, the integer. When we declare a variable as an integer, we are telling the compiler the piece of memory that this variable uses is going to be interpreted as an integer value. When you give an object a value, the compiler and CPU take care of encoding your value into the appropriate sequence of bit for that data type. Okay, so fundamental data types. C++ comes with built-in support for many different data types. These are called fundamental data types, but are often informally called basic types, primitive types, or built-in types. Here is a list of fundamental data types, some of which you have already seen. So these ones, I'm guessing they don't need a library. You can just start using them. No, I think standard library is included in fundamental data types. Okay, so char, boolean, float, double, long double, char 8, char 16, char 32. What do you mean by integral? Floating point, integral, null pointer, void. This chapter is dedicated to exploring these fundamental data types in detail, except null pointer, which we will discuss when we talk about pointers. C++ also supports a number of other more complex types called compound types. We will explore compound types in a future chapter. The terms integer and integral are similar but have slightly different meanings. In mathematics, an integer is a number with no decimal or fractional part, including negative or positive numbers and zero. In C++, the term integer is most often used to refer to the int data type which holds integer values. However, it is also sometimes used to refer to a broader set of data types that are commonly used to store and display integer values. This includes short, int, long, 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 and their signed and unsigned variant. Most programming languages include a fundamental string type. In C++, strings aren't a fundamental type, they're a compound type. Many of the types defined in the newer version of C++ uses a T suffix. This suffix means type, and it's a common nomenclature applied to modern types. What's the definition of nomenclature? It hold on. Let me see. Nomenclature meaning. The devising or choosing of names for things, especially in science or other disciplines. So nomenclature is like how you're choosing to name things. Many of the types defined in the newer version of C++ uses a T suffix. If you see something with a T suffix, it's probably a type, but many types don't have a T suffix, so this isn't consistently applied. Okay, let's open the next chapter. It's about void. Oops. I meant to do this. And I don't know why the PDF isn't opening. Void is the easiest of the data type to explain because void means no type. Void is our first example of an incomplete type. An incomplete type is a type that has been declared but not yet defined. The compiler knows about the existence of such types but does not have enough information to determine how much memory to allocate for objects of that type. Void is intentionally incomplete since it represents the lack of type and thus cannot be defined. Void value won't work. Variables can't be defined with incomplete type, void. So void in is used to show that the function does not return a value. Deprecated functions that do not take parameter. Although this will compile in C++, The use of the keyword void is considered deprecated in C++. The following code is equivalent and preferred. Okay. Other uses of void. The void keyword has a third more advanced use in C++ that we will cover in section 19.5. We're in chapter 4, so this is quite far ahead. Okay, next chapter, object sizes and the size operator. Uh, uh, because we typically, wait, hold on. A single object may use 1, 2, 4, 8, or even more consecutive memory addresses. The amount of memory that an object uses is based on its data type. Because we typically access memory through variable names and not directly via memory addresses, the compiler is able to hide the details of many bytes of a given object uses from us. When we access some variable x in our source code, the compiler knows how many bytes of data need to be retrieved and will output the appropriate machine language code to handle that detail for us. There are several reasons it is useful to know how much memory an object uses. First, the more memory an object uses, the more information it can hold. A single bit can hold two positive values, 0 and 1. 2-bit can hold four positive values. 3-bit can hold 8 possible values, and so on. To generalize, an object with n bits can hold 2 to the power of n unique values. Second, computers have a finite amount of free memory. Every time we define an object, a small portion of that free memory is used for as long as the object is in existence. Because modern computers have a lot of memory, this impact is usually negligible. However, for programs that need a large amount of objects or data, the difference between using 1 byte and 8-byte objects can be significant. New programmers often focus too much on optimizing their code to use as little memory as possible. In most cases, this makes a negligible difference. Focus on writing maintainable code and optimize only when and where the benefit will be substantive. Fundamental data type sizes. The obvious next question is, how much memory do objects of a given data type use? Perhaps surprisingly, the C++ standard does not define the exact size in bits of any fundamental types. Instead, the standard says the following. An object must occupy at least 1 byte. A byte must be at least 8 bits. The integral type char, short, int, long, and long have a minimum size of 8, 16, 16, 32, and 64 bits respectively. Char and char 8 are exactly 1 byte, at least 8 bits. When we talk about the size of a type, we really mean the size of the instantiated object of that type. A byte. In this tutorial series, we will present a simplified view by making some reasonable assumptions that are generally true for modern architectures. A byte is 8 bits. Memory is byte addressable. Floating point support. Yeah, I don't understand this. We are on a 32-bit or a 64-bit architecture. Given the above assumption, we can easily state the following. So Boolean is 1 byte. Typical size is 1 byte. Character char 1 byte. W char 2 or 4. Char 8 is 1 byte. Char 16 bits. Char 32 bits. Short 2 byte. Int 4. Long 4 or 8. let's say 4 bytes, and then long long has 8 bytes. Wait, hold on. Uh, okay, wait a minute. Let me take a picture of this, copy and close, and then paste it here. Then expand it. Now I want to remember this, so let's just test it. So Boolean is, hold on, I'm just checking my avatar. Okay, Boolean is 1 byte. Can I actually, hold on. Good. No, this won't work. Anyways, this is 1 byte. I'll use by. Why is this not working? by equal to byte and then capital B is equal to bit. So 1 byte or 8 bit. Maybe I should type it in text. One byte. Char is also 1 byte, right? One byte. W char is 1 byte. One byte. This is 8 bits, also 1 byte. This here is 16 bits, so 2 bytes. 32 bits, so 3 byte. Hold on. Hold on, I'm confused about something. No, this is 4 bytes. Hold on. 2 to 1 byte can hold 8. 2 byte can hold 16. 3 byte can hold 24. I don't know why I got so confused. So a short is 2 byte, I think. Yeah. Wait, but an integer is also 2 bytes. In order to determine the size of the data types on a particular machine, C++ provides an operator named sizeof. The sizeof operator is a unary operator that takes either a type or a variable and returns the size of an object of that type. You can compile and run the following program to find out how large some of your data types are. Set W is like set W 16, 16 width. Hold on, let me go here. STD cout. Size of is part of the IO stream, or is it a built-in thing? Size of jar, and then new one. Int. If I go to tools, how do I check which version of C++ is this? There is a way. I think it's in tools, but I'm not completely sure. Let's see. Application, build and run. Project settings. How do I figure out which C++ version I'm using? Because I remember I changed it to version 17. File, project, maybe. So let's just run this and see what we get. There's a notification here. Okay, so it says 1 and 4. Hold on. I'm assuming it's on bytes. So 1 byte. Okay, so in my compiler uses this as 4 bytes. Let's see what it says for everything else. So int short long long. I think it's float maybe. What's the difference between float and float t? Double. I think these are both for decimal points. Char. I don't know what W char is for. Is it char W? No. W char underscore T. Then char 16 underscore T. Okay, 16 and 32, that stuff is obvious. Shouldn't this take 1 bit? Why would it take an entire byte? Or, yeah, if it can't go less than a byte, then it has to take up 1 entire byte, right? Float, double, long double, float, double, long double. Characters. Integers. This floats. Now let's run. Too many characters in constant. Oh, whoops. I was just waiting there for it to build. Why does it automatically add a space? Okay, so Boolean is 1 byte. Character is 1 byte. W character T. What is W character? One, 2 byte. Why is this? Okay, 2 byte. Int is 4. Long is 4. Long is 8. But why would I use int or long? So float double is 8. Long double is also 8. So short is, okay, in my system, short is 2. Int is 4. Long is 8. Long is 8. I think in some other systems, there might be a difference in int and long. It's not exactly clear to me why. To determine the size of data types on a particular machine, C++ provides an operator named sizeof. The sizeof operator is a unary operator that takes either a type or a variable and returns the size of an object of that type. You can compile and run the following program to find out how large some of your data types are. Okay, so for their in their system it's 112448488. Oh, I mean they're using C++17 as well. Your results may vary based on the compiler. Trying to use sizeof on an incomplete type will result in a compilation error. You can use the sizeof operator on a variable name. This is to see how many bytes the variable is taking. Is there a way to see the bits inside the variable? In On modern machines, objects on a fundamental data types are fast, so performance while using or copying these types should generally not be a concern. I want to see what the bits are in that variable. Signed integer. Wait, let me search this online. How to view bits of a variable C++. Forget it. I will just view it later because laptop takes a long time loading. An integer is an integral type that can represent positive and negative whole numbers, including 0. C++ has 4 primary fundamental integer types: short int, long int. This is typically 32 bits on modern architectures. I think these two were different, but then they changed int to be 32, and then they changed and then they introduced long int. Uh, so this is 2 bytes. This is also 2 bytes. This is 4 bytes, and this I'm assuming is 8 bytes. Technically, the Boolean and char types are considered to be integral types because these typically stores their value as an integer, as integer values. For the purposes of the next few lessons, we will exclude these types from our discussion. And all types integer values. When writing negative numbers in everyday life, we use a negative sign. For example, -3 means -3. The attribute of being positive, negative, or zero is called a number sign. By default, integers in C++ are signed, which means the number's sign is stored as part of the value. Therefore, a signed integer can hold both positive and negative numbers and zero. In this lesson, we will focus on signed integers. We will discuss unsigned integers, which can only hold non-negative numbers, in the next lesson. Here's a preferred way to define 4 types of signed integers. So you can type long. So you can type long as long int, but that's not preferred. You can type short as short int, but that's not preferred. The integer type can also take an optional signed keyword. Signed short, signed int, signed long. Wait, if I don't say signed and I sign the value -4, what happens then? Int x -4 signed int y -5 std cout x y, and then as practice I will just write new line. This is signed. -4 and -5. How do I check the range of this? Like, what's the maximum and minimum? Do I have to calculate that? This keyword should not be used as it is redundant, or since integers are signed by default. So 8-bit sign goes from 1 minus 128 to 127. 16-bit signed 132,768 to 32,767. Okay. For the math inclined, as n-bit signed variable has a range, an n-bit signed interval has a range of -2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. I think the nth bit is used to indicate the sign itself. For what happens if we try to assign the value 140 to an 8-bit signed integer? The number is outside the range that an 8-bit signed integer can hold. The number 140 requires 9 bits to represent uh, 8 magnitude bits and 1 sign bit. But we only have 8 bits. In C++, 20 standard makes this blanket statement. If during evaluation of an expression the result is not mathematically defined or not in the range of representable values for its type, the behavior is undefined. Colloquially, this is called an overflow. Therefore, assigning the value 140 to an 8-bit signed integer will result in undefined behavior. If an arithmetic operation such as addition or multiplication attempts to create a value outside the range that can be represented, this is called integer overflow. For signed integers, integer overflow will result in undefined behavior. Assume 4 byte integers. Wait, hold on. This is signed by default. No. I did not know we can add this apostrophe in numbers. Integer overflow, undefined behavior. Let's see what happens if I do 120 is 128. Wouldn't it give minus? Wouldn't it like loop around? Because I'm assuming that the highest value is just discarded. Oh, sorry, now 128. I should say short. Isn't this outside the range? Or is 128 the last? 8-bit signed. Or is it assuming that it's unsigned? Hold on, let's just choose a very large number. How is it giving? So X is 2 bytes. How is it outputting 122, 1280? 7. Let's see what it does now. Okay, this fails the compiling. Compiling failed again. Now let's see. Conversion from int to short requires narrowing conversion. What if I do minus? Okay, if someone has an explanation of why this works, just let me know then. Okay, so int x is this, cout int, then integer overflow. What's the highest value int can store? 16-bit signed. Well, on our computer it's the same as long, so I think it's this. So if we do x plus 1, we get an integer overflow or undefined behavior. This goes to the 2's complement, right? Like this happens because of 2's complement. In general, overflow results in information being lost, which is almost never desirable. If there is any suspicion that an object might need to store a value that falls outside its range, use use a type with a bigger range. Okay. Uh, Integer division. When dividing two integers, C++ works like you would expect when the quotient is a whole number. So 20 divided by 4 is 5. Now 8 divided by 5 is giving 1. When doing divisions with two integers called integer division, C++ always produces an integer result. Since integers can't hold fractional values, any fractional portion is simply dropped out. Take a closer look at the above example. 8 divided by 5 produces the value 1.6. Well, 1 is the quotient as 3 and 3 is the remainder, right? So it drops the remainder. What would the range of a 5-bit signed integer be? A 5-bit signed integer can support 2 to the power of 5, 32 unique values. For a signed integer, these are split almost equally amongst positive and negative value, with negative receiving an extra value. So the range would be minus 16 to 15. Wait, hold on. So the first bit, 2, 4, 8. Together they can store 8 values. 2 values together, 4 values, and then 3 of them 8. Yeah, 16, 32. Then this bit represents a negative, the sign, right? So there are uh, 32 values you can represent. So from 0 to 32 if it's unsigned. Then minus 16, 15 if it is signed. Hold on. No, wait. It can represent 32 different values. 2, 4, 6, 8. Yeah, it goes from 60 to 31. 1, 2, 3, 4, 5. 2, 4, 8, 16. 32. So 32 values. If you include 0, then the values goes from 0 to 31. These are 32 different values. Yeah, that makes sense. So 13 divided by 5. 5 times 2 is 10 and the remainder is 3, but the remainder is dropped. Only the quotient, that is 2, is left. So minus 2. Okay, let's see unsigned integers. And why to avoid them? Unsigned integers are integers that can hold non-negative whole numbers. So the range 8-bit unsigned 0 to 255. 16-bit unsigned goes from 0 to 65535. Okay, so basically, like there's a negative and positive part. Uh, since the number of values they can hold is the same, then they shift it, like do plus 16 on both sides. We do plus 16 on both sides, then we get 0 and 31. If you want to change unsigned to signed, then do minus that many amount on both sides, minus half of it, minus half to what the most significant bit, then the number of values uh, number of values this can hold. So for example, 2, 4, 8, 16, 32. This can hold 32 different values. So 0 from 0 to 31. Half of 32 is 16. So subtract 16 from both sides. We get minus 16 and 15. These are the values a signed version can hold. And these are the values the unsigned version can hold. Unsigned integer overflow. So I'm guessing if you If you take this number and you have x is 31, then x plus 1 would be 0, because 31 would basically be 1, 1, 1, 1, 1. If you add 1 to this, all of these will become 0. The answer is integer overflow. Oddly, the C++ standard explicitly says a computation involving unsigned operands can never overflow. This is contrary to general programming consensus that integer overflow encompasses both signed and unsigned use cases. If an unsigned value is out of range, it is divided by 1 greater than the largest number of the type, and only the remainder is kept. The number 280 is too big to fit in our 1 byte range of 0 to 255. 1 is greater than the largest number of the type. 1 greater than the largest number of the type is 256. Okay, so the largest number is 255. 1 greater than this is 256. Therefore, if we divide 280 by 256, getting 1, remainder 24, the remainder 24 is what is stored. Wait, they don't store the quotient? Okay, so largest 16-bit unsigned value possible in unsigned short. Okay, 65535. And then you do 65536. It's out of range, so we get a modular wrap. So it goes to 0. 35537 is out of range and we get a modular wrap. Oh, I see what they're doing. Let's see. They said they use C++17, right? Because I remember setting the version to C++17. So minus 12 will wrap around to 0. The 65535, and then minus 2 will be 65534. Many notable bugs in video game history happen due to wrap around behavior with unsigned integers. In an arcade game, okay, never mind that. The controversy over unsigned numbers. So why doesn't this modular wrap work with signed numbers? Many developers believe that developers should generally avoid using unsigned integers. This is largely because of two behaviors that can cause problems. First, with signed values, it takes little work to accidentally overflow the top or bottom of the range because those values are far from 0. With unsigned numbers, it is much easier to overflow the bottom of the range because the bottom of the range is 0, which is close to where majority of our values are. Consider this a fraction of two unsigned numbers such as 2 and 3. How long will this take? Oh, there's no ST. Wait. So in this example, they're doing 2 minus 3. prints this long number. -1 can't be represented as an unsigned integer, so we get an overflow, and the following result is this. Another common unwanted wraparound happens when an unsigned integer is repeatedly decremented by 1. Warnings are treated as errors, right? So this won't compile. Truncation from int to unsigned short. Okay, how about this? We do +1 +1 again. Or we can just do it here. X +1. Another common unwanted, can't this issue happen with signed integers as well? Or maybe because in the negative part, the fact that we have a negative, I don't understand. Another common unwanted wraparound happens when an unsigned integer is repeatedly decremented by 1 until it tries to decrement to a negative number. Wait, hold on, this works. Or maybe, wait. Oh no, this would work because, yeah, this, because it's not storing the answer in X. Let's try this. Okay. 65535, X is now 0. Wait, so if I have signed, what's the largest value X can hold? The size is 2 bytes, right? And so that's 16 bits. So the signed value has the range. Signed value can hold 65536 values. So range is 65536 divided by 2. 32768 minus, so let's put this here. Let's see what happens now. Oh, and now it wrap around. If I do this and then minus, Okay, it wraps around now. Because the values are far from zero, because like both the ends are far from zero, people prefer using the signed value because you can have a negative. Second, and more insidiously, unexpected behavior can result when you mix signed and unsigned integers. In C++, if a mathematical operation has one signed integer and one unsigned integer, the signed integer will usually be converted to an unsigned integer, and the result will thus be unsigned. For example, unsigned int, signed int, u minus 3 will produce this result. In this case, if u was signed, the correct result would be produced. But because u is unsigned, which is easy to miss, S gets converted to unsigned. Here's another example where things can go wrong. So signed minus 1, unsigned 1, if S is smaller than u, which is true. But since it's comparing, it will convert minus 1 to this very large number. This program prints 1 is less than negative 1. This program is well formed and compiles and is logically consistent to the eye, but it prints the wrong answer. I see. I guess this is why you should avoid unsigned. Additionally, there are other problematic cases that are challenging to detect. Consider consider the following: void do something unsigned int x, run some code x times. Okay, so do something minus 1. The author of do something was expecting someone to call this function with only positive numbers. But the caller is passing in minus 1, clearly a mistake. What happens in this case? The signed argument minus 1 gets implicitly converted to the unsigned parameter. Minus 1 isn't in the range of an unsigned number, so it wraps around to 4294, well, this long number. And the program goes ballistics. Because you have to run the code x times. Given the above problem, the somewhat controversial best practice that we will advocate for is to avoid unsigned types except in specific circumstances. So when should you use unsigned numbers? There are still a few cases where it's okay. First, unsigned numbers are preferred when dealing with bit manipulation. They're useful when well-defined wraparound behavior is required. Second, the use of unsigned number is still unavoidable in some cases, mainly those having to do with array indexing. We will talk about this in the lessons on arrays and array indexing. Also note, if you're developing for an embedded system or some other processor or memory limited context, use of the unsigned numbers is more common and accepted for performance reasons. Okay, I guess that makes sense. Okay, so next chapter is fixed with integers and size t. An int has a minimum size of 16 bits, but it's typically 32 bits on a modern architecture. If you assume an int is 32 bits because that's most likely, then your program will probably misbehave on architectures where int is actually 16 bits. Since you will probably be storing values that require 32 bits of storage in a variable with only 16 bits of storage. On the machine where int is 32 bits, so x may be 16 bit or 32 bit, x, this overflows if int is 16 bits. Okay, if int is 32 bits. Oh, so x will print different values based on the machine bits. X, okay, yeah, I get the general idea. In most cases, we only instantiate a small number of int variables at a time, and these are typically destroyed at the end of the function in which they are created. In such cases, wasting 2 bytes of memory per variable isn't a concern. However, in cases where our program allocates millions of int variables, wasting 2 bytes of memory per variable can have significant impact on the program's overall memory usage. Why isn't the size of integer types fixed? The short answer is that this goes back to the early days of C, when computers were slow and performance was of utmost concern. C opted to intentionally leave the size of integers open so that compiler implementers could pick a size for int that performs best on the target computer architecture. That way, programmers could just use int without having to worry about whether they could be using something more performant. Fixed width integers. To address the above issue, C++11 provides an alternative set of integer types that are guaranteed to be the same size on any architecture. Because the size of these integers is fixed, they are called fixed width integers. The fixed width integers are defined in the cstd int header as follows. So int 8. Oh, they use the t thingy, t suffix, when you're importing types from other libraries. So int 8 has 8 bits, int 16 has 16 bits, 32 bits, 64 bits. So standard integer, C standard integer. Use a fixed with integer type when you need an integral type that has a guaranteed range. Warning, std int 8 and uint 8 typically behave like characters. Due to an oversight in C++ specification, modern compilers typically treat std int 8 and uint 8 uh, the same as signed char and unsigned char, respectively. Thus, on modern systems, 8-bit fixed with integral types would behave like char types. For fixed with integers, import this int 8 type, initialize 8-bit integral type with value 65. You're probably expecting this to print 65. Yeah, I am. Hold on. I just want to check something. In C++, integral is the same thing as integer, right? Although you're probably expecting the above program to print 65, it most likely won't. Okay, let's see. Where do they define integral? Uh, so I want to run this program. The term integral means like an integer. Most often, integral is used as part of the term integral type, which includes a broader set of types that are stored in memory as integers, even though their behavior might vary. So, integral includes uh, a Boolean, no, not Boolean, yeah, Boolean character, an integer. Okay. Okay, it produces a, capital A, because it's treated like a character. Other fixed width downsides. The fixed width integers have some potential downsides. First, the fixed width integers are not guaranteed to be defined on all architectures. They only exist on some systems where they are fundamental integral types that match their width and following a certain binary representation. Your program will fail to compile on any such architecture that do not support a fixed width integer that your program is using. First, for fixed First, the fixed width integers are not guaranteed to be defined on all architectures. But isn't it the library that matters? Like, if it's not defined, then I can just import this, right? However, given that modern architectures have standardized around uh, 8, 16, 32, and 64-bit variables, this is unlikely to be a problem. Oh, I know what they mean. So if it's like 5-bit, then the fixed width integers won't be able to use them. Second, if you use a fixed width integer, it may be slower than a wider type of some architectures. For example, if you need an integer that is guaranteed to be 32 bits, you might decide to use std in 32, but your CPU might actually be faster processing 64-bit integers. However, just because the CPU can process a given type faster doesn't mean your program will be faster overall. Modern programs are often constrained by memory usage rather than CPU, and the larger memory footprint may slow your program more than the faster CPU processing accelerates it. It's hard to know without actually measuring. Fast and least integral types. To help address the above downsides, C++ also defines two alternative set of integers that are guaranteed to exist. Fast type, int fast, and uint fast provide a wait. Is there a hash in the name itself? Provide a fast, signed, and unsigned integer type with a width of at least. Oh, I got confused. Where hash is 8, 16, 32, or 64. For example, std int fast32 will give you the fastest signed integer type that's at least 32 bits. By fastest, we mean the integral type that can be processed most quickly by the CPU. The least types provide the smallest signed and unsigned type with a width of least hash bits. For example, stduint least32 will give you the smallest unsigned integer that's at least 32 bits. Wait, I don't understand. Can't you just do u in 32? Wouldn't the least 32-bit integer be at least 32 as well? So least 8, least 16 is 32. So fast 8. So this brings 8 bits. So the fastest integer that is at least 8 bits. And this is the fastest integer that is at least 16 bits. And this here represents the fastest type that is at least 32 bits. So 8, 32, 32. So their CPU processes 32 bits faster than 16. 8. What's the point of this though? I don't understand. Wouldn't least 8 be the same as int 8? Because int 8 is the least number of. Because in int 8, the least number of bits would be 8, right? Because the size of fast least integers is implementation defined, your program may exhibit different behaviors on architecture where they resort to different sizes. Avoid the fast and least integral types because they may exhibit different behaviors on architecture where they resolve for two different sizes. Okay, let's do this. This is going to take forever. What's this? Wait. Let's see what I get. 8, 16, 32, 8, 32, 32. I still don't understand the least stuff. Given the various pros and cons of the fundamental integral types for the fixed width integral types, the fast least integral types, and unsigned challenges, there is little consensus on integral best practices. Our stance is that it's better to be correct than fast, and better to fail at compile time than runtime. Therefore, if you need an integral type with a guaranteed range, we recommend avoiding the fast least types in favor of the fixed width types. What is std size t? Consider the following code. See out size of int. On the author's machine, this prints 4. Pretty simple. We can infer that operator size of returns an integer value, but what integral type is that return value? An int is short. The answer is that size of returns a value of type std size t. Std size t is an alias for an implementation defined unsigned integral type. In other words, the compiler decides if std size t is an unsigned int, an unsigned long, and so on. Std size t is an alias for an implementation defined unsigned integral type. It is used within the standard library to represent the byte size or length of the object. Std size t is defined in a number of different headers. If you need to use std size t, C standard def is the best header to include, as it contains the least number of other defined identifiers. All right. Much like integer can vary in size depending on the system, std size t also varies in size. Std size t is guaranteed to be unsigned in at least 16 bits, but on most systems will be equivalent to the address width of the application. That is, for a 32-bit application, std size t will be typically 32-bit unsigned integer. So is size t defined here as well? Std size t. Let's see what I get. No, wait, I need size of. Size of. Why is size t a different color from this? So this is 8 bytes. So size t on my computer is 8 bytes. Assumingly, you can we can use the size of operator to ask for the size of size t. Compile as a 32-bit console app on the author system. This prints 4. Size t imposes an upper limit on the size of an object. The size of operator must be able to return the byte size of an object as a value of type std size type. Therefore, the byte size of an object can be no larger than the largest value size type can hold. Let's assume that std size t has a size of 4 bytes on our system. An unsigned 4-byte integral type has range 0 to 4 billion or 4 million, right? 4 million. No, 4 billion, sorry. Therefore, a 4-byte size T object can hold any value from this range. Any object with a byte size of this range could have its size returned in a value of type size T. So this is fine. However, if the byte size of an object were larger than these many bytes, then sizeof would not be able to return the size of that object accurately, as the value would be outside the range of std size T. Therefore, no object larger than these many bytes could be created on this system. But what if you have a very large string? What if you have something? Then how does it print all this? How many bytes? It size of this takes 35 bytes, right? If you have a very large string, would it be able to print? Introduction to scientific notation. Scientific notation is a useful shorthand for writing lengthy numbers in a concise manner. Numbers in scientific notation take the following form: significant times 10 to the power to significant significant times 10 to the power of whatever exponent. For example, in the scientific notation, 1.2 times 10 to the power of 4, 1.2 is the significant and 4 is the exponent. This evaluates to 12,000. By convention, in the scientific notation are written with one digit before the decimal point. The rest of the digits afterwards. Consider the mass of the Earth. In decimal notation, we would write this as this large number. That's a really large number, too big to fit even in an 8-byte integer. It's also hard to read, even with these separators. The number is still hard to read. In scientific notation, this would be written as 5.9722 times 10 to the power of 24, which is much easier to read. Scientific notation has the added benefit of making it easier to compare the magnitude of two extremely large or small numbers by simply comparing the exponents. Okay. Because it can be hard to type or display exponents in C++, we use the letter E or sometimes capital E to represent it. To represent the times 10 to the power of part of the equation. For example, 1.2 times 10 to the power of 4 would be written as 1.2 E4. 5.9722 times 10 to the power of 24 would be written as 5.9722E24. For numbers smaller than 1, the exponent can be negative. The number 5e minus 2 is equivalent to 5 times 10 to the power of minus 2, or 0.05. Okay, let's say you need to know the value of the mathematical constant pi for some equation, but you have forgotten. You ask two people. One tells you value of pi is 3.14. The other tells you the value of pi is 3.14159. Both of these values are correct, but the latter is far more precise. Here's the most important thing to understand about the scientific notation. The digits in the significant, the part before e, are called significant digits. The more significant digits, the more precise a number is. In scientific notation, we would write 3.14 as 3.14E0. Since there are three numbers on the significant, this number has three significant digits. Okay. Handling trailing zeros. Wait. Don't you just get rid of the trailing zeros? When converting to scientific notation, trailing zeros after a decimal point are considered significant, so we keep them. 87.0 grams is the same as 8.70 E1. Okay, consider the case where we ask two lab assistants each to weigh the same apple. One returns and says the apple weighs 87.0 grams. The other returns and says the apple weighs 87.000 grams. Let's assume the weighing is correct. In the former case, the actual weight of the apple could be anywhere between 86.950 and 87.049. Oh, so 87.0 and then plus and minus 0.05. No, 0.01, right? Actually, 0.05. Maybe the scale was only precise to the nearest tenth of the gram, or maybe our assistant rounded a bit. The latter case, we are confident about the weight of the apple to a much higher degree. Okay, so if the zero is significant, then we include it in our notation. Okay, why isn't this opening? C++ has three fundamental floating point data types: a single precision float, a double precision double, and an extended precision long double. Wait, if I keep going back, Size of no back. More back. Yeah, yeah. On modern architectures, floating point types are conventionally implemented using one of the following point formats: IEEE 754 standard. Yeah, I will view this later. Float is almost always 4 bytes and double is almost always 8 bytes. I want to remember what the long double here was. Wait, to change this to string. Let's see. 488. Right. On the other hand, long double is a strange type. On different platforms, its size can vary between 8 and 16 bits. We recommend avoiding long double. They keep saying IEE 754. I need to read about this off stream. Maybe I can do it now. Here are some definition of floating point variables. When using floating point literals, always include at least one decimal place, even if the decimal is 0. This helps the compiler understand that the number is a floating point number and not an integer. 5 means integer, 5.0 is a floating point literal. No suffix means double type by default. 5.0 is a floating point literal. The F here means a float type. 0 is an integer, 0.0 is a double. So this is a double, this is a floating point, this is a double. Wait. Always make sure the type of your literals match the type of the variables they're being assigned to or used to initialize. Otherwise, an unnecessary conversion will result, possibly with a loss of precision. In the first case, stdcout printed 5, even though we typed 5.0. By default, stdcout will not print the fractional part of a number if the fractional part is 0. In the second case, the number prints as we expect. In the third case, it printed the number in scientific notation. So when does it do scientific notation? When it sees like 5 decimal places? Hold on. IEEE 754 is a technical standard for floating point arithmetic, originally established in 1985 by the Institute of Electrical and Electronic Engineers. A floating point format is specified by a base p, which is either 2 binary or 10 decimal, a precision p, and exponent range from e minimum to e max. So I want to know about C++ specifically. Floating point precision. Consider the fraction 1 over 3. Decimal representation of this number is 0.3333, with 3's going up to infinity. If we write this number on a piece of paper, your arm would get tired at some point. On a computer, an infinite precision number would require infinite memory to store. We typically only have 4 or 8 bytes per value. This limited memory means floating point numbers can only store a certain number of significant digits. Any additional significant digits are either lost or represented imprecisely. The number that is actually stored may be close to the desired number but not exact. The precision of the floating point type defines how many significant digits it can represent without information loss. The number of digits of precision of a floating point has depends on both the size and the particular value being stored. For example, a float has 9 to 6 digits of precision. This means that a float can exactly represent any number with up to 9 significant digits. A number with 7 to 9 significant digits may or may not be represented exactly. Double values have between 15 and 18 digits of precision. A floating point type can only precisely represent a certain number of significant digits. The following program shows stdcout truncating to 6 digits. When outputting for floating point numbers, stdcout has a default precision of 6. What happens if I do uh, whoops. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so it represents properly. Now both of these have to be the fraction. Wait, this, and then I want to this, and then y. Okay. So if one of them is a double, then it's fine, I guess. You can override the default precision that stdc out shows by using output manipulator function named std set precision. Okay, so this is an output manipulator. Shows 17 digits of precision. Okay, let's try. IO manip or manipulate. IO manipulate. So if you set precision once, it sets the precision for all future outputs, right? Output manipulators are sticky, meaning if you set them, they will remain set. One exception is set W. Some input output operations reset set W. So set W should be used every time it is needed. What is set W? Is this also about precision? Okay, let's see. So set precision 9 and this is 9 2. 1 2 3 4 5 6 7 8 9 and 2. So over here it says 1 2 3 4 5 6 7 8 9 and 0. 1 2 3 4 5 6 7 9 2 is greater than 1 2 3 4 5 6 7 8 9. The value 1 2 3 4 5 6 7 8 9.0 has 10 significant digits, but float values typically have 7 digits of precision. And the result of this is precisely only to 7 significant digits. We lost some precision. Favor double over float unless base is at a premium. Rounding errors make floating point comparisons tricky. Floating point numbers are tricky to work with due to non-obvious differences between binary and decimal numbers. Consider the fraction 1 over 10. In decimal, this is easily represented as 0.1, and we are used to thinking of 0.1 as an easily representable number with one significant digit. However, in binary, the decimal value 0.1 is represented by the infinite sequence. Because of this, we assign 0.1 to a floating point number. We will run into precision problems. We will see the effects of this in the following program. So we have double 0.1 here. Use default CR precision of 6. And then if you set precision to 17, you get this. The top line stdc out prints 0.1 as we expect. On the bottom line where we have stdc out shows us 17 digits of precision. We see that D is actually not quite 0.1. This is because the double had to truncate the approximation due to its limited memory. Also in binary, representing 0.1 will take like infinite values, right? Rounding errors can have unexpected consequences. So we are adding 0.1 many times then we end up with 0.99999. Over here it's 89. Although we might expect that D1 and D2 should be equal, we see that they are not. If we were to compare D1 and D2 in a program, the program would probably not perform as expected because floating point numbers tend to be inexact. Comparing floating point numbers is generally problematic. One last note on rounding errors. Mathematical operations such as addition and multiplication tend to make rounding errors grow. So even though 0.1 has a rounding error in the 17th significant digit, when we add 0.1 10 times, the rounding error has crept into the 16th significant digit. A corollary of this rule: be wary of using floating point numbers for financial or currency data. Inf represents infinity. Nan, which stands for not number. There are several kinds of nan. Unsigned 0, meaning there are separate representation for positive 0 and negative 0. Formats that are not compatible with IEEE 754 may not support some of these values. In such cases, code that uses or generates these special values will produce implementation-defined behavior. So 5.0 divided by 0 is positive infinity. This is negative infinity. It's positive 0, negative 0, and 0 divided by 0 is not a number. So inf, negative n, 0, negative 0, nan. Note that the result of printing in and nan are platform specific, so your result may vary. Okay, let's see this in Visual Studio. The following warning is treated as an error. Potential divided by 0. Oh, I can't output this. Okay, never mind then. So Boolean values. I think I will read about set W off stream. I don't know what's happening. Boolean values are variables that can have only two possible values, true and false. To declare a Boolean value, use the keyword bool. Okay. Just as the unary minus sign minus operator can be used to make an integer negative, the logical not operator can be used to flip a Boolean value from true to false. This will make it false, this will make it true. They are stored as integral values. True is stored as an integer 1 and false is stored as an integer 0. Similarly, when Boolean values are evaluated, they don't actually evaluate to true or false. They evaluate to the integer 0 or 1 because Boolean store integer values. They are considered to be an integral type. When we print Boolean values, stdcout prints 0 for false and 1 for true. Use std alpha to print true or false. If you want cout to print true or false instead of 0 or 1, you can output std alpha. This doesn't output anything but manipulates the way stdcout outputs the bool value. Here's an example. Okay, so std alpha, this will be true or false. You can use no bool alpha to turn it back off. Integer to Boolean conversion. When using uniform initialization, you can initialize a variable using integer literals 0 and 1, but you really should be using false and true instead. Other integer literal cause compilation errors. So this is okay, initialize to false. So okay, initialize to true. Error narrowing conversion disallowed. So B false, B true, and B no. In any context where an integer can be converted to a Boolean, the integer 0 is converted to false, and any other integer is converted to true. So this only causes error during initialization. Otherwise, a non-zero integer would be seen as true. This wait, std bool alpha b1 for std b1, then std out b2. So true, false. This is seen as true because it's a non-zero. This as false is because it's seen as 0. Inputting Boolean values. Inputting Boolean values using stdcin sometimes trips new programmers up. Consider the following programs. Cout enter a Boolean value. Cin you entered. Okay, so if they enter true, it says you entered 0. By default, Cin only accepts numeric inputs for Boolean variables. 0 is false and 1 is true. Any other numeric value will be interpreted as true and will cause Cin to enter failure mode. Any numeric value will be interpreted, any non-numeric value will be interpreted as false and will cause Cin to enter failure mode. Wait. Any other numeric value. So if I input 4, it will be seen as true and then Cin will enter failure mode. Otherwise, any non-numeric value will be seen as false and Cin will enter failure mode. In this case, because we entered true, Cin silently failed and set B to false. To allow Cin to accept words false and true are as inputs, you must first input to std bool alpha. So set bool alpha and then we can get true or false. However, when stdable alpha is enabled for input, numerical values will no longer be accepted. Okay, so 1 or 0 won't work anymore. And they only allow lowercase. Boolean values are often used as the return values for functions that check whether something is true or not. Such functions are typically named starting with the word is. So consider the following example. So Boolean is equal. So it's okay. So if the return type is Boolean, it's like a yes or no question, right? Here's output from 2 runs of this program. 5 and 5, 5 and 5 are equal here. Then 6 and 4 are equal false. Okay. So if statements. The simplest is if statement takes the following form. If condition and then the statement. For readability, this is more often written as if condition and then statement. A condition, also a conditional expression, is an expression that evaluates to a Boolean value. Sample program using an if statement. So x equals to 0. Then output this value is 0. First, the user enters an integer. Okay. The condition x is equal to 0 is evaluated. The equality operator equal is used to test whether two values are equal. Operator equal returns true if the operands are equal and false if they are not. Since x has value 0 and 0 is equal to 0 is true, this expression evaluates to true. Because the condition has evaluated to true, the subsequent statement executes, printing the value is 0. If statements only conditionally execute a single statement. I mean, we can allow curly brackets, right? We can allow another scope. Given the above example, what if we wanted to tell the user that the number they entered was non-zero? So the value is 0, and then if it's not equal, the value is non-zero. Both of these programs are far more complex than they need to be. Instead, we can use an alternative form of a statement called if-else, if condition else statement. Okay, since I'm familiar with this, I will just rush through. Now our program will produce the following output. Enter 0, and then the value is 0 because this is true. Now you enter 5, then this is false, and that means the value is non-zero. Chaining if statements. Sometimes we want to check if several things are true or false in sequence. We can do so by chaining an if statement to a prior if else, like so. If x is more than 0, and then statement. Else if x is less than 0, and then statement, and then else, and then the final statement. Boolean return values and if statements. We wrote this program using a function that returns a Boolean value is equal. Let's improve this program using an if statement. So if is equal, then x and y are equal, else x and y are not equal. Okay, non-Boolean conditions. In all of the examples above, our conditions have been either Boolean values, true or false, Boolean variables or functions that return a Boolean value. What happens if your conditional is an expression that does not evaluate to a Boolean value? In such a case, the conditional expression is converted to a Boolean value. Non-zero values will get converted to Boolean true, and zero values will get converted to Boolean false. Okay, so over here the if statement will pass. So this will be evaluated as true. A return statement that is not the last statement in a function is called an early return. Such a statement will cause a function to return to the caller when the return statement is executed. An unconditional early return is not useful. Std out a and return, and then all of this is redundant. Since std out b will never be executed, we might as well remove it. However, when combined with if statements, early returns provide a way to conditionalize the return value of a function. So absolute value, if x is less than 0, then multiply it by -1. Otherwise, return x as it is. When abs 4 is called, x has value 4. Okay, get it. Okay, let's do question 3. How can the length of the following code be reduced without changing the format? So, if is allowed to take fun ride, have fun, else sorry, you're too short. So stdc out, how tall are you? Double height, stdc and height. Height is more than 140, return true. Can't you just return this? Instead of writing return 2, return false. Write return height is more than or equal to 140. I don't think you just return the height, right? No, actually, return this. You don't need an if statement and is allowed to take fun ride. The expression evaluates to a blue, which can be returned directly. Yeah, that's what I was saying. Okay, so characters. A character data type was designed to hold a single character. Character can be a single letter, number, symbol, or white space. The character data type is an integral type, meaning the underlying value is stored as an integer. Similar to how a Boolean value 0 is interpreted as false, a non-zero is interpreted as true. The integer stored by character variable is interpreted as an ASCII character. Character literals are always placed between single quotes. Here's a full table of ASCII characters. Wait. ASCII stands for American Standard Code for Information Interchange, and it defines a particular way to represent English characters as numbers between 0 and 127. So 0 is null, 33 is this exclamation mark, 34 is this code, 66 is capital B. So if we have 65 stored in binary and we print it to the console, then we get capital A. Also 40, the numbers as characters is different from the numbers as integers. So 48 in ASCII is like 0 as text. Codes 0 to 31 and 127 are called unprintable characters. These codes were designed to control peripheral devices such as printers. Most of these are obsolete now. If you print these characters, the results are dependent upon your OS. Codes 32 to 126 are called printable characters and they represent a letter. You can initialize a char variable using character literals. So char character A. You can initialize char with integers as well, but they should be avoided if possible. So this 97 is converted into the letter A. Hold on. If I char A character I get A, but then what happens if I do this is 97, right, in binary, so this should be the letter B. Okay, it outputs 98. It outputs as a number. I think it converts to integer when it does addition. Be careful not to mix up character numbers with integer numbers. The following two initialization are not the same. Initialize with integer 5, initialize with the code 0.5, stored as integer 53. So this is the preferred way, and it will output A. This is not preferred, and it will output its associated character, which is B. The following program asks the user to input a character, then prints out a character. Here's the output of the program. Note that cin will let you enter multiple characters. However, ch can only hold one character. Consequently, only the first input character is extracted into variable ch. The rest of the user input is left to the input buffer that cin uses and can be extracted with subsequent call to cin. You can see this behavior in the following program. So cin character CHA and BCD is left queued. The following cin doesn't ask the user for input, it grabs the queued input. Okay, let's see this. Why is it in two lines? Okay, if I run this. No, wait. Hold on. So if I do A, you entered A, and then it's asking for an input again. Right. Okay, I'll just do but if I do, I think I tried this last time, like this, and it does A and S, because there's still some uh, characters in the input buffer. Because extracting input ignores leading white space, this can lead to unexpected results when trying to extract white space characters to a char variable. Assume the user enters A space B without quotes. Extract A leaves B in stream. Skips the leading white space. Extracts B. Okay. Uh, but because the leading white space is skipped, we extracted the B character instead. One simple way to address this is to use the stdcin.get function to perform the extraction instead, as this function does not ignore leading white space. Cin.get jar. Okay, let's see. Cin.get character this and this. If I do this, I get C and X as expected. If I run again, S space D, I get space as the second input. Hold on. S space D space A. Yeah. So it does S and then space and then D. Can I? Never mind. I was thinking of uh, outputting the corresponding integer, like the represent the binary as an integer, but we haven't done that yet. So char size, range, and default sign. Char is defined by C++ to always be 1 byte in size. By default, a char may be signed or unsigned. If you're using char to hold ASCII characters, you don't need to specify a sign. If you're using char to hold small integers, something you should not do unless you're explicitly optimizing for space, you should always specify whether it is signed or unsigned. A signed character can hold a number between -127 and -128 and 127. An unsigned char can hold a number between 0 and 255. But why would you use? I don't understand signed char. Wouldn't the ASCII code be the same? I don't understand the use of signed chars. There are some sequences of characters in C++ that have special meaning. These characters are called escape sequences. An escape sequence starts with a backslash and then a following letter or number. You have seen the most common escape sequence /n, which can be used to print a new line. There's a first line /n, second line /n. There's also /t, which is a tab, a horizontal tab. Slash single quote to print single quote, and // to print a backslash. Here's a table of all escape sequences. /a makes an alert such as a beep. /b moves the cursor back one space. Yet what happens if I let's see. If I do /b, would it override the R to capital I? Yes, it did. What happens if I do /a? Shouldn't there be any alert? What does /a do? So /v prints a vertical tab. What's a vertical tab? So it's like multiple new lines. We printed an emoji. So, so /number translate the char represented by an octal /x translated into char represented by a hex number. XF in hex is char O. What's the difference between putting symbols in single and double quotes? Text between single quotes is treated as char, which represent a single character. Text between double quotes is treated as C-style string literal, which can contain multiple characters. Avoid multi-character literals. For backwards compatibility reasons, many C++ compilers support multi-character literals, which are char literals that contain multiple characters. For example, 5, 6 in single quote. If supported, these have an implementation defined value. Because they are not part of the C++ standard and their values not strictly defined, multi-character literals should be avoided. Multi-character literal support sometimes causes problems for new programmers. Cout add 1 2 and slash n. Or they made a mistake. On the author's machine, it inputs 312142. The issue is here. The issue here is that the programmer accidentally used /n, a multi-line character literal consisting of a forward slash, instead of \n. The program first prints 3 correctly, but then it prints the value of /n. It is implementation defined as 12142. Here is another example. This program outputs exactly as you expect. The value of x is 5. But this output isn't nearly exciting enough. So we decide to add an exclamation point before the new line. Or we added 2 characters instead. What about other char types? WCharT, char 8, char 16, char 32. Much like ASCII maps the integers 0 to 127 to American English characters, other character encoding standards exist to map integers of varying sizes to characters in other languages. The most well-known mapping outside of ASCII is the Unicode standard, which maps over 144,000 integers to characters in many different languages. Because Unicode contains so much code points, a single Unicode code point needs 32-bit to represent a character. char 16 and char 32 were added to C++ 11 to provide explicit support for 16-bit and 32-bit Unicode characters. These char types have the same size as uinteger least 16 and uinteger least 32. Char 8 was added in C++ 20 to provide support for 8-bit Unicode. It is a distinct type that uses the same representation as unsigned integer. You won't need char 8, char 16 or char 32 unless you're planning on making your program Unicode compatible. wchar should be avoided in almost all cases except when interfacing with the Windows API, as its size is implementation defined. They don't elaborate what wchar is. I think wchar is like, okay, so the size is implementation defined. Yes, that's the definition of wchar. Okay, introduction to type conversion. This is what I was searching for. In the above example, print 5 as a parameter of type double, but the caller is passing in the value 5, which is of type int. What happens in this case? Most cases, C++ allows us to convert values from one fundamental type to another fundamental type. The process of converting a value from one type to another type is called type conversion. Thus, the int argument 5 will be converted to double value 5.0 and then copied into parameter x. By default, floating point values whose decimal part is 0 print without the decimal point. When the compiler does type conversion on our behalf without us explicitly asking, we call this implicit type conversion. The above illustrates this. Nowhere do we explicitly tell the compiler to convert integer 5 to double value 5.0. Even though it is called a conversion, a type conversion does not actually change the value of the type of the value being converted. Instead, the value to be converted is used as input and the conversion results in a new value of the target type. Also, there's like a 5 literal stored here, and then there's a 5.5 literal stored here as well. The conversion does not change the variable y from int to double. Instead, the conversion uses the value of y as input to create a new double value 5.0. Implicit type conversion warnings. Although implicit type conversion is sufficient in most cases where type conversion is needed, there are few cases where it is not. Consider the following program, which is similar to the example above. So void print int x int main, we have 5.5. In this program, we have changed print to take an integer parameter, and the function call to print is now passing in double value 5.5. Similar to the above, the compiler will use implicit type conversion in order to convert double value 5.5 into a value of type int so that it can be passed to function print. Unlike the initial example, when this program is compiled, the compiler will generate some kind of warning about the possible loss of data. Because you have treat warnings as error turned on, the compiler will abort the compilation process. Note that although we passed in value 5.5, the program printed 5. This is when the treat warnings as error is turned off. 5.5 is implicitly converted to an integer, so the fractional part goes away. Some type conversions are safe to make, such as int to double, whereas others may result in a value being changed during conversion, such as double to int. This is one of the primary reasons brace initialization is the preferred initialization form. Brace initialization will ensure we don't try to initialize a variable with an initializer that will lose value when it is implicitly type converted. So brace initialization will cause an error over here. An introduction to explicit type conversion via static cast operator. Back to our most recent brain example. What if we intentionally wanted to pass a double value to a function taking an integer? Knowing that the converted value would drop any fractional component, turning off treat warnings as error just to make our program compile is a bad idea, because then we will have warnings every time we compile, and we risk overlooking warnings about more serious issues. C++ supports a second method of type conversion called explicit type conversion. Explicit type conversion allows the programmer to explicitly tell the compiler to convert a value from one type to another. To perform an explicit type conversion. In most cases, we will use static cast operator. The syntax looks like this. Okay. So static cast int explicitly convert double value 5.5 to integer. Whenever you see C++ syntax that makes use of angle brackets, the thing between the angle bracket will most likely be a type. Because we are now explicitly requesting that double value 5.5 be converted to an int value, the compiler will not generate a warning about a possible loss of data upon compilation. So char 97, this prints a. If you want to print the integral value, oh, that's what I was asking before, we can use static cast int, then this will print 97. If the value being converted can be represented in the destination type, the converted value will remain unchanged. Only the type will change. Hold on. Unsigned int u1 is 5. So u1 is converted to signed int. This prints 5. Int s2, convert value of s2 to an unsigned int. This will, in both cases, is 5. Since the value 5 is in the range of both signed int and unsigned int, the value 5 can be converted to either type without issue. If the value being converted cannot be represented in the destination type, if the destination type is unsigned, the value will modulo wrap. If the destination type is signed, the value is implementation defined prior to C++20 and will be modulo wrapped as of C++20. So we have -1. If you do unsigned wrap, we get 492, 4967295. Here we have an unsigned integer. And if we do int, it will get modulo wrap. Now what if we do this? We are using C++ 17, right? We let's run this. Oh, we still get -1. Converting an unsigned integer value to a signed integer value will result in implementation defined behavior. std int 8 and std u int 8 likely behave like chars instead of integers. Now that we have covered what chars are, we can demonstrate where this can be problematic. So int 8, my integer is 65, then stdc out, and then it will output a character. It will print a. However, this is not guaranteed on some system. It may actually print 65. If you want to ensure that std int 8 or std u int 8 object is treated as an integer, You can convert the value to an integer using static cast. Okay. Wait, hold on. So here they entered a number between 0 and 127, and the input is 35. Okay. So 35 is treated as a character. I don't know what's happening. No, wait. It's inputting C in is getting 3 as a character. Okay, let's see what's happening. When std int8 is treated as a character, the input routine interpret our output as a sequence of characters, not as an integer. So when we enter 35, we are actually entering two characters, 3 and 5. Yeah, I think 51 is the code for 3. Because the character object can only hold one character, 3, 5 is left in the input stream for possible extraction later. Because the character 3 has an ASCII code point 51, the value 51 is stored in my int. Okay. Write a short program where the user is asked to enter a single character. Print the value of the character and its ASCII code using static cast. So we only need IO stream, right? So character value, right? And then you input it std cin dot get value, and then std cout slash n value, and then space, and then static cast. Is this part of the, wait, is this built in or is this part of IO stream? Static cast int va return 0. How do I cancel the current build? dn 100. Wait. std cout input character Oh wait, I'm looking at the answer. I mean, wait, did a single character? Yes, they did what I did. But character, let's say A, and then I get 97. What happens if I just press enter? The build takes so long. It output 10. I think 10 is like the enter character. Okay, chapter 4, summary and quiz. The smallest unit of memory is a binary digit. The smallest unit amount of memory that can be addressed directly is a byte. Okay. Sign, is there something that's confusing me? Nope. The quizzes get more challenging starting here. These quizzes that ask you to write a program are designed to ensure you can integrate multiple concepts that have been presented throughout the lessons. Here are some tips. Don't try to write the whole solution at once. Use the debugger and go back and review the answers. I don't think they're too difficult for me because for a new programmer it might get difficult, but it's not too difficult for me. So I would use a switch case, but I don't think they introduce switch cases. Okay, here they have to implement an equation. Okay, I get the general idea. So next stream I would be doing, or any stream here, next stream I'll be doing chapter 5, maybe 6 as well. And this is an optional chapter between 6 and 7. It's about bit manipulation, but I want to learn that too. Yeah, so we'll end the stream here. And I guess I will see you next time.